Good morning, students. Let's start today's session. So we are doing CCNA-1, Introduction to Networks. So far, we have finished 6 modules, and today we are going to do module number 7, which is Ethernet switching. Ethernet is a special kind of local area network with specifications laid out by IEEE. Okay, so let's go and study about switching in Ethernet. We'll be looking at what the Ethernet frame looks like, what are the different fields and layers, what is the Ethernet MAC address, MAC as in the NIC hard-coded address. We'll be looking at the MAC address table, okay? Specifically, the MAC address table that is existing in the switch and how it updates that table. And we'll also look at switch speeds and forwarding methods. Start with Ethernet frames. So Ethernet, as I told you, is a special kind of local area network, okay? And it operates in the data link layer, layer 2, and the physical layer, okay? And information about this you can find in IEEE 802.2 and 80.2.3 standards, okay? The details about this you can find in 802.2 and 802.3 standards. With regards to the data link sublayers, we have studied this before. We have got the LLC sublayer, logical link control, and the MAC sublayer. Information about logical link control is in IEEE 802.2, and MAC sublayer is IEEE 802.3 and 802.11 and 802.15. Okay. MAC sublayer is responsible for your data encapsulation. Okay, and the MAC, that is your media access control, and it provides the MAC addressing, okay, the hardware address of your NIC. So let's look at the MAC. This sublayer, the MAC sublayer, as you can see, okay, is responsible for a few things, and that main things are, okay, data encapsulation. So data encapsulation, how does it happen? Okay, these 3 steps: Ethernet frame, Ethernet addressing, and Ethernet error detection. Ethernet frame, as in the internal structure of the Ethernet frame. Ethernet addressing, it tells the Ethernet frame what would be the MAC address. That means what is the MAC address to deliver, and what is the MAC address that you come from. actually the source and the destination address. And if there is any error, okay, there will be an FCS. That FCS, a frame checker sequence, is used for detecting error. So depending on what kind of media you use, your Mac sublayer can have different kinds of technology. It can be uh, half duplex. It can be full duplex. Okay. So sometimes if you're using an old technology, which is obsolete, we don't use. In the olden days, we were using, in terms of bus topology, we used to use uh, hubs or perhaps uh, half duplex medium. So in those situations, remember we studied CSMS-CD. In those situations, you're using a half duplex media, okay? But most of the technology that we have today is we don't have hubs anymore. Even if you look for them, you can't find them. What we use is a switch. A switch is a full duplex communication, okay? And we don't need to do CSMA-CD anymore, okay? Uh, remember we studied CSMA collision uh, detection and collision avoidance, okay? So in today's world, most of the switch that we use is a full duplex communication, okay? So our Ethernet standard that we have, okay, can be through all these, you see, over fiber or copper, okay, is mostly full duplex communication. Now, how does the frame look like? Okay, the minimum size is 64 bytes. Minimum size, okay, and the maximum is 1518 bytes. So in the beginning, you have got the start frame delimiter, the SFD, which is 8 bytes. And then you have got a destination MAC address, which is 6 bytes, another 6 bytes for the source MAC address. Now remember, when you say the MAC address is, remember the numbering system we studied? This is a base 16 hexadecimal address. This is a base 16 hexadecimal address, okay? So you have to have the source MAC address and the destination MAC address. And then what kind of data you're carrying? 2 bytes. And your actual data will be between 45 and 1500 bytes. And right at the end, 4 bytes is given to your frame check sequence. Okay, so this will ensure that there is nothing wrong with your frame. Okay, now it says over here 45 to 1500 bytes. Now what happens is sometimes when you get more than 1500 bytes, okay, in those situations we call it jumbo frames, okay, when you get more than 1500 bytes. So let's go into Ethernet MAC addresses. So as we studied, a MAC address is a hardware address. Every NIC has got a MAC address. Every device has got a MAC address. And that address is permanent and hardware coded, and it's a hexadecimal value. Okay? So it consists of 48 bits. When you say 48 bits, Okay, 48 bits means how many bytes? Divided by 8, that would make it 6. Yes, thanks, Cassandra. That would make it 6 bytes. Okay, if it makes it 6 bytes, so when you talk about hexadecimal, okay, you know that in hexadecimal, to represent 1 byte, you have to use 2 hexadecimal values. So to represent 6, you will need 12 hexadecimal values. Okay? So keeping that in mind, remember, your MAC address and your IP version 6 address is always represented by using hexadecimal values. Okay? So if you want to represent a binary, this one is binary 000000000. Decimal would be 0. This one is 1111111. Okay? So in decimal, if you want to represent this, this will be 2, 5, 5. Okay? How do you represent this in hexadecimal? It would be FF. Okay? So how do you represent the binary 0001010? So you break it into 2 halves as we studied. So this one is 0, 1010 is A. So the correct representation of this binary value is in hexadecimal 0A. Okay? Another thing you should remember that the hexadecimal number is often represented by a 0x precedence. Okay? So you know that this is a hexadecimal value. When you say hexadecimal, remember it is a base 16. Okay? So your MAC address is a 48-bit binary value represented in a hexadecimal value. Okay? Consisting of 6 bytes, and you will have 12 hexadecimal values. Something like this. You see 6 bytes. 1, 2, 3, 4, 5, 6. Okay? Now, each of these consists of 2 hexadecimal values. So that's why 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 hexadecimal values come together and make 6 bytes of hexadecimal values. Now, the question is, why your hexadecimal address is divided into 2 halves? Can you see 3 bytes are called OUI, and the other 3 bytes is vendor assigned? Think about it. Why? If you think about it, you will realize that every NIC, every hardware NIC that we have is supposed to be unique. That means every device, IoT device, computers, mobile devices, switches, routers, anything that you think of which has got a network interface card inside it should have a unique hexadecimal value. There shouldn't be any repetition. So how is that assigned? It's very simple. What happens is, if I want to set up a new factory and manufacture my own network interface cards, I can do that. But I have to go first to IEEE. Okay? and register with IEEE and get a unique 6 hexadecimal code called the organizational unique identifier. So I should get 3 bytes from IEEE. So that ID, IEEE will tell me, okay? For example, they will say, what is the name of your organization? I'll say I'm going to create a new electronics called, let's say, Foad Electronics. They'll say, okay, so the first OUI of your Foad Electronics will start with these 6 values, these 6 hexadecimal values. So henceforth, anything coming from my factory, Foad Electronics, will have these 6 OUI. And then I will add another 6 hexadecimal values based on what I want. This is dependent on me. This is given by IEEE. Get it? That way, every equipment that is manufactured by me, okay, every network interface card, even if I manufacture IoT devices, smart TVs, and anything that has got network interface card in it, will have a unique MAC address. No repetition. Okay? That is how every device that we have has got a unique MAC address. Okay? No MAC address is repeated. Okay? So you have to get your OUI from the from IEEE, registering from IEEE. And then once you have got the OUI, then the other 3 bytes will be dependent on you and what you give. Okay? What address you give. So when you are sending a message in your Ethernet, okay, your Ethernet header will consist of a source MAC address and a destination MAC address, as you can see over here. So you have got where it has come from and where it has to go. Okay? So when this message, when this frame is traveling in the network, when it comes across every NIC, the NIC will check the MAC address and see whether it matches its own MAC address. If there is no match, it won't accept it. And if there is a match, it will accept it. Okay? So now imagine how many NICs are you surrounded with right now. Think about it. Literally, any device that is on a network has got a NIC. Okay? And in an Ethernet, whatever device is on that network has got an NIC. So if the frame has got the destination address and it matches the NIC that it's going to, it will accept that frame. Otherwise, it will reject it. Now, when you send data, okay, we have studied that in a network, we have got unicast, multicast, and broadcast. So in your Ethernet, we have got different MAC addresses, fixed MAC addresses for unicast, broadcast, and multicast communications. So unicast is very straightforward. You send your address to a destination, MAC address, just mention the MAC address, okay? And then it goes to that MAC address. For example, this is your source computer consisting of this MAC address, and this is your destination consisting of this MAC address, okay? So IP version 4 address is here of this source, and IP version 4 address of the destination. So there is another thing you should know. There is an association between your IP version 4 address and your MAC address, okay? And that association, okay, that association that this IP address is associated with this MAC address is known as address resolution protocol. This is only for IP version 4. The association of MAC address with IP version 6 is called neighbor discovery. Okay? So, whenever you send from a source MAC to a destination MAC, remember the source will always be a unicast. But the destination can be broadcast, can be unicast, can be multicast as well. Okay? So here you can see our Ethernet frame will have a destination MAC, have a source MAC. In the network layer, the packet, it will ask for a logical address. So in this case, IP version 4, it will consist of a source IP address and a destination IP address. Now let's build upon that. So a unicast address, as we studied, the source unicast is always unicast. But the destination can be unicast, can be multicast, can be broadcast. So what is a destination MAC address? Let's say if a destination MAC address of FF is in hexadecimal, what does it relate to? Okay. So in situations like that, when you get this kind of destination address, you see, 12 hexadecimal values, all F. That means in binary, it is all going to be 1, 1, 1, 1, 1, 1, 1. Correct? That means you are sending a broadcast. You see over here? This means you are sending a broadcast. That means you are sending your frame from here to all the computers in the network. Okay? You can just try it out. Go to your calc. Okay, a programmer calc. Okay, so I go to hexadecimal. In hexadecimal, I type 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There. Look at the binary value. Translation. Okay, so it's all 1, 1, 1, 1, 1, 1, 1. Okay. So keeping that in mind, if this is your destination, you immediately know that this is a broadcast frame. Okay. And remember, this is hexadecimal. In your logical address, your broadcast is always 255. Okay. Remember, when you give an IP address, it has to range from 1 until 2, 5, 4. Why not 255? Because 255 is reserved for broadcast. Okay, there. This means you are sending your frame to every computer in the network. So maybe I shouldn't use the word computer. Every device in the network. Okay. So what does that mean? Okay, that means, look over here. It says, interestingly, it says, if the encapsulated data is an IPv4 broadcast packet, this means the packet contains a destination IPv4 address that has all ones in the host portion. What does that mean? That means if you are sending to a destination 192.168.1, you see the last octet you are saying 255. This means it's going to send to all the computers where the host portion is 111. What is the host? For example, this computer, look, it is 192.168.1.10. What is the subnet mask? 255.255.255.0. So network portion is 24 bits. Host portion is 0. So we are interested in the network portion. That means it is going to send to all the devices in the network that have got this 111 portion. So it will send it to this device, 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 okay? Because all of them, the network portion is 111, because we're interested in the network portion. So that's what sending a broadcast means. You send it to all the devices in the network. And in IPv4, broadcast is 255. And in your hexadecimal, this is how you represent it. Okay? Multicast means you send it to a series of computers, not all the computers. Okay? It's a group of devices. Okay? So, if your destination MAC address is 01005E, okay, 01005E, if it starts with these 3 bytes, then you know that you're sending multicast. Okay? Here you see, in IPv4, multicast, the group of devices will have a specific IP address. Okay? So, in this situation, when you are sending, when it is 0105E, then you know that it is an IPv4 multicast address. But if the destination is 3333, then you know it's IPv6 multicast address. Okay? So multicast is a group of computers that share the addresses. Okay? Wait a minute, there's a question. Yes, Cassandra. Cassandra is asking a question. She's saying that broadcast can be done within the same network. Yes, you're right. Broadcast is always within the same network. In fact, a router is known as a broadcast killing machine. Okay? Your broadcast will never go outside the router. Okay? Your broadcast is always within the same network. Okay, moving on. Now let's look at the MAC address table. Did I miss something? No, okay. So there is a actual table in our switch machines, okay, which tells us what is the MAC address of each computer that is connected to me. And that table is known as the MAC address table. Okay. Now, this is something that you have in every switch. Okay. Uh, there's a correspondence of the MAC address with the logical uh, IP address. So if it's IP version 4, we call it ARP. And if it is IP version 6, we call it network discovery. Okay. So every time you connect a device to your switch will examine its MAC address and then take that MAC address and build a table inside it. And every time it needs to access that device, that machine, it looks at the MAC address in the MAC table, okay, and accesses the machine, okay. When the first time you switch on your switch, your MAC address is empty. And then as it detects activity messages between devices, the MAC address will get filled up. Okay. So you can call your MAC address table a CAM table as well. Content addressable memory. The switch, in fact, when you switch it on, is in a learning mode. It checks for all the new devices that are connected to it, and based on that, it can know what is the MAC address of these devices. If in future, when it wants to refer to any of these devices, it will look at that MAC address. If the MAC address, for example, is a new device, the MAC address does not exist, it will add it to the table. Okay. And it will keep maintaining that entry for 5 minutes. Every 5 minutes, it will refresh it. Okay. Uh, Actually, we can try this out. Let's have a look. Okay, I take a switch, a 2960 switch. Enable. Okay. So let's look at the MAC address table. Show MAC address table. Now you can see the MAC address table is empty. I haven't created any VLAN. The default VLAN will always be VLAN 1. But you see, look at the MAC address table of this switch. If you look over here, the MAC address table is empty. Now let's do something interesting. Let's add a computer here. Let's go and add a PC. Connect the PC to the switch. Okay. Here I go. Fast Ethernet 0. Connected to the switch. Fast Ethernet. Now we go back to the, we go back to the switch. Now again, show MAC address table. You see it's still empty. So I go now to my PC and give an IP address. Okay. I give an IP address to my PC. So here it goes, 192.168.1.10. Okay, subnet mask is given. There. Now, again, I go and check my MAC address table. There, you see, I have an entry. Can you see, my dear students? Look at the MAC address 0001437C C376. Does this match my PC's MAC address? Let's have a look. Let's go here. We go to the command prompt and we type ipconfig/all. Okay. So let's look at the PC's MAC address. There, the physical address 001-437C. Now match it to your. Does it match? Can you see there is a match? Can you see, my dear students? Okay. So this is your switch's MAC address table, having information of all the MAC connected to the network. Okay. Run it again. You see, it disappears. Now, I'm going to make it appear again by adding another device to the network. Let's say another PC. Okay, another PC connected to fast Ethernet 0 to fast Ethernet 2. Give an IP address. .192.168.1.11. Subnet mask is given. Okay, now let's go to the switch. Again, show MAC address table. Okay, once again, show MAC address table. It shows the new device. Okay, let's go and check over here. CMD, IP config/all. Just check the address. Look at the physical address and look at my switch. You see 005, 005, 5EB4, 5EB4, C0E7, C0E7. Can you see it? Okay. Now, let's do a show MAC address table again. There, it's gone again. Now, what I'm going to do is I'm going to do a ping so that it again builds up the MAC address. Okay, I'm going to ping from my PC A to PCB. Ping 192.168.1.11. Okay, sending a ping. There, the ping is successful. Now let's go to the switch and give the same command. Show MAC address table. There, can you see? It again builds up the MAC address table. Okay, amazing, isn't it? And it shows you what are the MAC addresses connected to the switch. Okay, so you get an inkling of how your MAC addresses work. Now that you have got this MAC addresses, okay, every time you want to, the switch has to refer to that MAC address, it will look for a match in its table. If the match is found, okay, it will forward the frame to that device. So this is how it's done. Every device that you connect to the switch, Okay, that device MAC address will be in your switches table, MAC address table. Okay, it will also say to which port it's connected. The MAC address table will also have information about which port it is connected. Okay, so when you want the switch to find that device, it can just refer to the MAC address and the port connectivity, and it can send the data to that directly. Okay, specifically in unicast or even multicast, it will be faster. Now let's go to the switch speeds and forwarding methods. Now switches follow two main ways of forwarding data. Okay, we know that there is a table where it stores all the devices MAC address, but there are two specific ways that it sends data. The first one is store and forward switching. Okay, in this store and forward, it will receive the entire frame and then forward it. You know, it has got option to ensure that everything in the frame is okay, the CRC, cyclic redundancy checks and all that. If there's any issue, it will fix it. Once it has made sure the frame is perfect, everything is okay, then it forwards it. That's right, store and forward switching. We also have a cut-through switching. There is no storing, okay? It is received and forwarded, okay? So there is no actual check. So perhaps in situations where you are doing a voice transfer in real time, and you need your QoS, your quality of service, to be paramount, then perhaps you should go for store and forward switching. Okay, rather than cut through switching. When we look at cut-through switching, again, cut-through switching, there are two kinds. There is fast-forward switching and fragment-free switching. Fast-forward switching, as the name suggests, the frame is immediately sent, forwarded to the destination. Okay? But in fragment-free switching, there is a little bit latency. So it takes a little bit, it incorporates a little bit algorithm of store and forward switching, okay? To make sure that it does some check. It doesn't check the whole thing. It checks the first 64 bits. Sorry, the first 64 bytes, okay? It checks the first 64 bytes. Because usually if there is an error, it is in the first 64 bytes. If it finds an error, then it fixes it. Okay? Because usually they say errors and collisions happen in the first 64 bytes. So this is your fragment-free switching. So if you're doing an Ethernet switch and you're using a buffering technique, okay, so these memory buffering techniques can be port-based memory or shared memory, okay? In port-based memory, frames are stored in queues, and a frame is transmitted to the outgoing port only when all the frames ahead in the queue have been successfully transmitted. In shared memory, it deposits all the frames into a common memory buffer shared by all the switch ports. So these are the two differences. So we have got two kinds of settings, duplex settings on an Ethernet network. One is full duplex and one is half duplex. Okay. Now, we already studied that half duplex is something that we used in old devices and old machines, specifically in the bygone era of using hubs. Okay. Most of the switches that we use are operating on a full duplex mode. Okay. So when you have devices connected to each other, you should ensure that there is no duplex mismatch. If you're using an old switch, which is working on a half duplex mode, specifically connecting that port to a port of a switch, which is full duplex, it will have a issue. Okay. I mean, the communication will still go on, but then it will be slower because this is full duplex. This one is half duplex. Okay. So it will not work with the same efficiency as a full duplex. So you have to be careful of that. So most of the switches we use actually is full duplex. Okay. Uh, so, but still, if you're in a network, as an engineer and you have got a network issue, the speed of the network is faltering or that is in question. So you have to actually have perhaps look at the network in that organization and see whether someone is using a half duplex switch, saving money or, so that could be one of the issues. And this is something that we have studied again before, but we'll study it again. Most of our devices, be it routers or switches, they have got auto-MDIX. Okay. And as per auto-MDIX, doesn't matter what kind of cable you use. It can actually, since it is auto-MDIX, okay, the device can automatically detect the type of cable and it will adjust the port configurations accordingly, automatically. Again, let's go to packet tracer so I show you this. Okay, look here. I'm going to have a new switch here. This is my switch and this is my PC. Now, we know that a PC to a switch is a straight through cable. Okay. Let's have another PC. Again, we know that a switch to a PC is a straight through cable. But now I'm not going to use straight through. I'm going to use a crossover. Connect to fast Ethernets 2. You see the connection is still existing. Okay, can you see? This is because of your auto-MDIX. It will enable that connection. Okay. The switch will automatically detect, as it says, the type of cable attached to the port and configure the interface accordingly. As you can see over here. Doesn't matter which cable you use. You see, the switch is smart enough to automatically configure. But this is something actually you can switch off or switch on. You see, I go here, I go to the switch. This is so interesting, you see. Let's say I want to test my students. I want to make sure that they don't use crossover cable. Okay, so I'm going to switch off that MDIX auto. Okay, for example, for this port, this is our fast Ethernet 2, correct? You see here what I do. Okay, enable conf t. Okay, so the interface that I'm interested in is fast Ethernet 2, if I'm not mistaken, right? So what I do is, by default, it's MDIX auto. So what I do is I say no MDIX auto. Okay, that's it. You see what happens here? Okay. Now, you see, we have an issue. Can you see that? It will not accept a crossover cable. So the only way it will accept is you have to remove this. You have to go and get a straight through and connect the straight through. Now it will accept. Okay? Because you have disabled the auto-MDIX. Now, why would you do that? If you want to enforce, for example, in your organization, you have to connect your devices properly as per the guidelines. Okay, you can do that, but you know, it doesn't. You don't have to do that because the devices are now smart enough to automatically adjust the ports. Okay, so but sometimes, you know, we may want to do this, enforce this on our switches so that we tell the students that you have to use a proper cable. Okay, or in an organization you can enforce this if the network engineer is very strict. He can enforce this to ensure that everybody follows the, you know, the guidelines, so that you cannot connect using a crossover to a switch. You have to follow the exact rules. You see, this one will not be accepted. Now I'm going to bring it back. Okay, again, I'm going to type over here. My previous command was no MDIX auto. Now I'm going to remove the no and just type MDIX auto. There, you see it's green already. Green, amber. After some time, it will be green. Okay. So this is another tip for you. So this brings us to the end of today's session. Anyone has any questions to ask? Okay, fine.